All right, everybody. Welcome to the Hardware System Collective seminar. Today's guest is Sherief Reda from Brown University. And Sherief's a full professor in the School of Engineering there. His interests are in energy efficient computing, design automation of integrated circuits, reconfigurable and embedded systems, and computer architecture. He's authored a couple books and a lot of articles, 120 articles. He's also had a number of best paper awards, like at DATE and ISLPED, and received an NSF Career Award a while back now.
Yeah, a long time ago, yeah.
So I'll hand it off to you. So.
All right. Thanks a lot, Matt, for the intro, and thanks for all the UC-SC team for inviting me today. It's actually pretty refreshing change from all the, from all the activities we mostly do confined to doing these days. So I changed the topic a little bit, not the topic, I changed the title a little bit compared to what I sent in the advertisements, but it's pretty much the same. So today I would be talking about our efforts in energy efficient design for adaptive approximate computing. All right. Why is it moving? Okay, do you guys see this? Now it moves? Did you see the size change?
Yes.
Yeah, all right, good. So I have a few slides first to introduce the topic before I start talking about our work in that area. And first, I want to make the case for approximate computing. Why should we pursue approximate computing? So if you look at the application landscape right now, there's so many applications that are basically data rich. They're relying on data for processing. And these include machine learning and, of course, deep learning, signal processing, computer vision, cognitive computing. And all of these applications have inherent error resilience in them. And that's basically what we can exploit for approximate computing. And this error resilience comes from a number of reasons, including the fact that these applications rely on sensors, and these sensors are inherently noisy, whether the input sensors are audio or video or things like gyroscopes and wearables, which I will talk about. These are all inherently noisy, and the algorithms in these fields have developed to handle this noise. It worked despite of that noise, so that shows you the inherent error resilience. The other reason is that these algorithms are approximate anyway. When you're having a sorting algorithm, that's exact. But when you have a deep neural network, that's an approximate algorithm. That nobody gives you a proof that the neural network will recognize all, I don't know, objects in some contract. All they give you is some classification accuracy for certain training sets and evaluation data sets. So the algorithms themselves, the engines for themselves are underlyingly approximate. There's also loose constraints on the outputs in the sense that sometimes the output, say for instance, like in this edge detection algorithm, there's lack of perception from humans whether the output is 100% correct or not. If you flip the intensities for some pixels or change their colors a little bit or change the audio output, it's not going to make a difference. So all of these characteristics of these applications make them amenable for approximate computing. And of course, if you look at the this is, for instance, the revenue from AI, and you can see the exponential growth in these applications. So these applications are here and they're going to dominate even more in the future. Now, what we want to do in approximate computing is to basically leverage this tolerance to error to create systems that are having much less power consumption. So for instance, in here, in these bars, let's say the original system has this high power and it has an error built in. All of these applications, like I said, classification accuracy of a DNN, it already has an error anyway. And then I can trade this system with another one where we basically can try to cut down the power consumption dramatically at the expense of maybe slight increase to error or a negligible increase to error or an error that has no effect on the user perception. So this is kind of the goal. And you can think of that, you can exploit that really in two ways. Let's say I have an original circuit, like on the one on the left. I can exploit approximate computing to design approximate circuit to do the same processing. Say I'm doing FFT or an FIR filter, or I'm doing some machine learning classifier and hardware. And I can create a system that has smaller design area, it has less power and less cost. Or I can actually, since I've now reduced the circuit, maybe I can deploy two of them. So I can, if I can squeeze the area and power by half, and I can deploy two, say, in parallel, and that's going to work within the same original power and design area budget. But now I have doubled the throughput. And basically, you can see this paradigm, for instance, in the Google Tensor Processing Unit. I think the difference between version 2 and 3 was pretty much that idea. So this is different ways you can exploit computing, approximate computing. So it's not necessarily for less energy. It could be for less energy or less power, but it can also means the same power, but double the throughput or more, of course. So what kind of hardware platform is the best to apply these approximations? So if you look at the hardware, platform landscape, you can use CPUs or GPUs or accelerators. And you can certainly have approximate CPUs and approximate GPUs and approximate accelerators, but which one is the best one? This was actually a study from Stanford a few years ago. They took the H.264 application and they tried to look at the power breakdown of the different units of this application. This was not related to approximate computing, but it shows you the point of, what is the best place. So when you look at something like a CPU, you will see that a majority of your power is basically gone in data transfer instructions, load and store, branches, incrementing, index loops and things like that. And eventually at the end of the day, the part that's really the number crunching that you're doing on the ALU is a very small fraction of your total power, maybe 10, 15% of your total power is there. So if I'm gonna do approximate arithmetic on a CPU, I'm not gonna really save a lot of power. I'm gonna save a very small amount. Basically, I'm limited to that 10, 15%. If you move to a GPU, that portion, the red portion, FU in here means functional unit. The portion that's going to be in your function unit is bigger because when you have a GPU, you have a SIMD-like architecture. And now I have more of these parallel ALUs running, crunching the data in parallel. So if I do have approximate modes for my ALUs in the GPU, I'll definitely get better bang for my buck in terms of the approximation value. Now, when you go to accelerator, you can start seeing that the functional unit now have a much major chunk of the power. Why is this happening? Because you're basically, you have basically eliminated a lot of the loads and the stores that you typically have in a regular computer. In a function accelerator, for instance, you can have something like a systolic array where the data is moving from one functional unit directly from the output of one to the input of another one directly. So basically you have much more of your system, your data path is composed of functional unit. And in addition, actually, I would argue, of course, that if you do deploy approximate computing there and you start reducing, for instance, the number of bits in your registers, then you're automatically even going to customize this data path even further, getting even additional benefits and power, meaning that you can get benefits and power consumption even in the movement of the data within an accelerator. It's much harder to do in a CPU because the CPU will just have like an approximate mode in its ALU, but the accelerator will be customly designed just to handle that. So I would say you can do them, but the best bang for the buck, I think, is your accelerator to do approximations within accelerators. Now, when you have accelerators for rich data applications, another opportunity come up. And what is that opportunity? And let's look at this diagram in here. At the beginning, I have some software, some machine learning classifier, for instance, running on my CPU or my GPU, and it consumes certain amount of power. And as I said, it's a classifier anyway, so it has some error to begin with. Now I design it as an accelerator and I get big reductions in power. That's the main advantage of accelerators. You have a custom accelerator, you get big reduction in power, and that hardware implementation is faithful to the original software, so you're getting the same error. Now, as I said, you can do approximations on the accelerator and you will get a big bang for your buck there. So your power goes down dramatically again, but the error could slightly increase. That's in the third part. And that's our approximate accelerator. But the interesting part in here is that you're designing an accelerator for a certain application. So it's like, say, an embedded system. In here, I can go do additional software, hardware co-design so as to mitigate that error in the hardware. So for instance, let's say you're having this simple classifier down there. Well, the classifier was determined based on weights. So maybe now I created some approximations on the hardware. Maybe I can compensate for these approximations by basically retraining my classifier. And as a result, I can actually change the weights and kind of compensate, flip that error back, and I reduce it back as in here. So I can create an approximate accelerator, which is blue, that would retain most of the power benefits of the original one and would bring me back the error down to almost the original implementation that I have. So that's one advantage, additional advantage of designing accelerator for rich data. You have that interesting software hardware co-design that you can use to kind of cancel out the approximations that you've done in the hardware. All right, so what you're really looking for in here is three intersections of three trends that I think are very powerful in what they bring. You have that rich data application. That's one big trend that's going to continue for us. And then we have approximations that we can do in our circuits and our system. And then you also have embedded processing and accelerator. That's another big trend we know, because we're not getting as much benefit from improving our CPUs anymore. So when you see those three intersections, if you basically look at that intersection point, that's really, I think, is the best systems where you can deploy these approximations. If you're designing accelerators for data-rich applications, then that approximations makes perfect sense in that domain. All right, so what is our goal? The goal of our work in the lab is to enable scalable, adaptive operation, energy efficient operation in the hardware and this hardware software by controlling this accuracy and the hardware resources like power. So for instance, in here, you see them that plot. I have the x-axis, the computational error, and then on the y-axis, computational resources, maybe like a hardware area, power, consumption, energy. And I want to be able to have this kind of scalable or adaptive operation. I can, at some time, I have a lot of energy, maybe in my battery. So in that case, I can have, I can consume a lot of power, but I have a small amount of error. Maybe later on, I don't have as much. So I'm allowed to basically consume less power, but increase my error. So we want to be able to have this adaptive approximate operation in runtime for these data-rich applications. If you have some background for students who have some background, took maybe the VLSI course, you might be wondering why you don't do voltage overscaling. So with voltage scaling, you're scaling up down the voltage, you know, as long as the critical path timing is okay. You don't have any negative slack. You don't have any failures. In voltage overscaling, you basically bring down the voltage even further. And that will introduce some errors in the computation because some of the critical path basically are not meeting their timing. But if you follow this approach, which has been proposed in the literature, it's not a good idea for a couple of reasons. One of them is the error can happen in the most significant bits. Let's say, for instance, I have this multiplier on the left-hand side. Where is the critical path? Well, the critical path is basically in the most significant bits. That's where you need all the carries to propagate there. So if during runtime, I dial down my voltage to bring down the power, yes, error will be introduced, but they will be introduced in the most significant bits. So that's going to be a big arithmetic error. You don't want this to happen. That's one reason why voltage overscaling is not a good idea. But there's even another bigger problem that the circuit might not work incorrectly because it can lead to metastability. So if I have these output and flip-flops, there is a chance actually I'm neither capturing a 0, I'm neither capturing a 1. I'm capturing this kind of in that metastable state. And my circuit actually failed altogether. It's not about having a wrong number. It's about just not working. So that's why we don't advocate using voltage overscaling as a way to dynamically introduce approximation or trade that with power.
Sherief, actually, question. I guess that's true for something like a ripple carry adder where the most significant bit is the critical path, but you can control that with different topologies, right?
In most
it doesn't have to be the most significant bit that's going to be an error when you scale down too much.
It's not like a low, but when we actually inspect most of the circuit, you would see that the most significant bits in many cases are the ones that actually are on the critical path, like multipliers, definitely for sure. Even if you don't have a ripple carry adder, even if you have like a carry look ahead or a CSA adder, and you would still, you know, all of the sums are coming out directly. You're doing the carries in some way. Right. So
actually, you're right. Yeah, I get it.
So that's why, but I think the metastability is the killer point, and that's why these approaches with voltage scaling basically don't go much over scaling because of that metastability, because it's not working anymore. So that's our goal in here. Any questions so far from the audience in here on this kind of like the big picture about this approach before I start talking in details about what we've been doing in that area?
So a little bit, maybe it's too much of a discussion, so tell me not to go over there. But one thing that I talked in the past with some people in the Soviet Union, when they were doing radars, they couldn't do fast multipliers. So what they were using is just the most significant bit as a max. But they still were having a lot of resolution for those things. You do a convolution using just the most significant bit with another, it works pretty decent. So have you compared, because that's a very simplified multiplier. It's a multiplier in which you just use the MSB on the multiplication. What is the trade-off there? For radar, it really works. I don't know, I have not seen for AI.
So actually,
what workload you're trying.
Yeah, so I was actually planning originally to talk about this. I had some in the abstract. I was talking about designing arithmetic modules, and I was planning to talk about the drum multiplier, which is a multiplier we had a few years ago. And the idea of the drum multiplier is basically something very similar to what you're saying. The drum multiplier, just in a nutshell, we've designed it well, as an ICCAD back 2015, was a test paper nominee. What we've done, let's say you're multiplying 16 bits. So what you do is you want to zoom in on the most significant bits, whatever they are. You basically want to find the leading one. So there are circuits that can find the leading ones. And the leading one in the extreme case is just the most significant bit, like you're saying. Not the most significant bit. You don't know where the most significant bit is. It's not like if you have a 16 bit, the leading one is not necessarily in bit 15. It could be in bit 13, 12, depending on what it is. So basically, drum would zoom in, find the leading ones in the both operands, and then it will say, I have a budget of 5 bits. So I will extract the 5 bits within the leading one, and then I will multiply those two numbers together, and then I shift them back to where they belong. So this idea definitely works, because if you can just identify the location of the most significant one in your number, then your error is at worst 2x the result. You're off by 2x the number, right? Because if I have a number like say 11, and I just truncate say the 1, then I'm gonna have an error by 3. But if you look at it, basically the sum of all the bits after that leading one can all add up to twice the number. So really, it's actually, it kind of justifies why this approach that you're talking makes sense, because it bounds the error in a big way. And that's basically was the idea on the drum multiplier. I was planning originally to talk about it, but then I thought maybe too much arithmetic for people. I thought I'd talk about more things that are, a little easier.
Okay.
Yeah.
Thank you.
Yeah. All right, so I have 3 ideas in here. As I mentioned, I was having 3 different subtopics to talk in the abstract, but I changed one of them. I thought maybe more people would be more interested in here. So I have a general approximate synthesis technique where you give it any circuit, and then how can you find the approximate version of that circuit? And then we talk about one that is application specific. If you have a particular application and you're doing approximation there, like say a deep neural network, it opens up the door for the software hardware co-optimizations. So that's interesting. That's different than general approximate synthesis technique. And then finally, I want to talk about end-to-end system co-optimizations and with approximate computing, in the sense that when you have a deep neural network or a circuit is not existing in vacuum, there's an end-to-end system, and typically in an embedded system, it starts with some sensor readings to finally a decision making. So I want to study a particular case on wearables, and in here you have accelerometer reading, you have feature extraction, you have a classifier, and then how can we do this end-to-end system co-optimization approximations across the whole system? So this is basically the 3 topics that I want to talk about going forward. So let's talk about the first one. So the tool for doing general approximate synthesis is a technique we came up with based on Boolean matrix factorization. So we're all familiar with matrix factorization, people who took linear algebra classes. I see something on the chat. Yep, somebody said floating basically. Something, yeah, it's kind of had that flavor of the idea. Yeah. All right, so if you have a matrix, like when you take linear algebra, you take matrix factorization, you have so many techniques, QR factorization, LU, SVDs, a lot of techniques for factorization. That's all fine. These are applied on matrices with real numbers. If you know your matrices actually are Boolean, meaning they consist of 0 and 1, there is matrix factorization techniques specifically designed for them. And they are lossy, actually, matrix factorization technique. So for instance, in here, this matrix M could be factored into 2 matrices B and C. And if you multiply B's and C's, you will get back M, except for one error, where that one is, we're highlighted in orange. Now, the interesting thing with Boolean matrices is really the multiplies are nothing but ANDs. You're just ANDing 2 bits. And the adds are nothing but ORs. So that actually simplifies the circuit that if you want to do Boolean matrix factorization, it's pretty simple, just ANDs and ORs. In terms of like if you're just trying to do the calculations. And one important thing in here is F, that's the factorization degree. F in here basically controls how smaller are B and C compared to the original matrix M. So for instance, F in here could be 1, that's basically multiplying a row by a column, or F is equal to 2, or F is equal to 3. And people have used this Boolean matrix factorization for basically document classification, language processing. And what we want to do is use this idea to synthesize approximate circuits. So I'll show you. This is the main idea in here. I'm going to take my original circuit, like in here, for instance, let's say I have a circuit with 3 inputs and 4 outputs, and I'm going to enumerate all the possible inputs. So I have 8 possible inputs, and for each one of those inputs, I'm going to find the outputs, the 4 outputs. So let's say you get this matrix M. So if you look at this matrix M, it doesn't have the inputs, it just has the outputs for each input combination. Here is the different outputs that will come out of this circuit. Then I can run one of the Boolean matrix factorization algorithms. We don't have space to talk about how is the factorization itself working, but there's algorithms for that. And if you factor it, you get those 2 smaller matrices. Now, and if you multiply them, you're not going to get the original matrix M. You're going to get one that is different, and the underlines in here are basically where the errors are happening. Now, the interesting thing is I can take this first long matrix B in my previous notation in here and basically synthesize it as a circuit. It's a circuit with 3 inputs. There are 8 rows in there, and it has 2 outputs. So I can take this truth table and basically synthesize it just with my traditional methods. And we call this the compressor circuit. And it's called the compressor circuit because compared to the original circuit, it's still taking 3 inputs, but it's producing 2 outputs instead of 4. So it's compressing the number of outputs into 2. Now, then there is another circuit based on the second matrix, which we call the decompressor circuit, that basically takes those 2 outputs and decompress them back into the original 4. The decompressor circuit is pretty easy because really, like, when you see 1, 0, what does this mean? It means basically the ORing of the first column multiplied by 1 with 0. So it's just the first column. So basically the first output in here is the same as the first output. Second column is 1 and 1. So it's basically saying OR those 2 outputs together. So the second output in here is the ORing of the compressed 2 outputs. The third one is 0, 0. So the third one is hardwired to 0. And finally, the fourth output is 0, 1. So this basically means it's equal to the second output in the compressor circuit. That's it. So, and we can control by F how big of a size we want for this compressor or decompressor. So F allows us to trade off basically the complexity of the circuit versus the approximations. So for instance, here's an original circuit. This is the truth table, 4 outputs. And I can do, for instance, factor with F is equal to 3. And I get a Hamming distance of 3, meaning that if you look at this truth table and compare it to the original circuit, you will see 3 bits got flipped. I can choose a factorization degree of 2. And if I do that, I get a Hamming distance of 6, but you can see things are basically like I have very simple truth tables. Or I can go all the way to a factorization degree of F equal to 1, and I get very simple compressor and decompressor, but the Hamming distance increases to 13.
So I have a question. So this is from just looking at the slides, but this compression, it will reduce the gates, but it will not focus on the critical path. Is that correct?
Yes, these are not focused on the critical path. So they will approximate the logic in general in the circuit. I haven't seen a case almost like we have results in one of our papers. I haven't seen a case where it led to an increase in the critical path because it's basically everything is just being, the logic is being pruned out of your circuit. So I haven't seen, I'm not saying there's approved. I mean, there is a chance maybe with F is equal to 3 and some weird scenario where you end up having a longer critical path, but it's very unlikely. In most cases, a smaller circuit.
Yeah, well, what I was not saying is that it will increase, is that the focus is to have a smaller circuit, but interesting on the approximation, it might be also it's okay to have more or less the same circuit, but give me a much higher frequency.
Yeah. Yep, exactly. So you can leverage that for that idea, and that would be kind of similar to that that idea that I mentioned earlier, is that you can exploit the smaller circuit to maybe two of them to have throughput. So similarly in here, what Jose is suggesting is that if I have a smaller circuit with a shorter critical path, then I can basically, I reduce the power by some factor, then I can crank up my frequency within the same voltage until I bring back, say, my slack to 0, and that way I have a smaller circuit but a higher performance.
Or reduce the voltage, it will have a quadratic effect.
Yeah, or you reduce the voltage and bring additional improvements to power. So that's definitely totally valid, yeah. So there's a beneficial cycle in here, additional round, if we're willing to say, to get either additional improvements in power or keep the power and crank up the frequency. Yeah. Thanks, yeah. All right, so here's another way of actually looking at what we're doing. Let's say I took this matrix and I factor it with 3, and I'm just having, I have the first column, let's factor it by 3. So the first matrix B is 8 by 3, and then the second matrix is 3 by 4. And, you know, if you look at how matrix multiplication is done, it's basically, there's a number of ways you can look at it. But one way is that it's equal to the multiplication of the first column by the first row. So that's basically gray times gray, and then darker gray by darker gray, and then darkest gray by darkest gray. And it's the ORing of all of them. It's a plus, but in here it's logic, so it's ORing. Now I can multiply each one of those columns and rows, and I basically have like 3 simpler truth tables. And that's basically, we call them, these are the factors. So basically in here, that would be factor. Here's a truth table factor. Here's another one, and here's another one. So these 3 factors now, we can combine them to increase the accuracy. So I can have, basically, you can think about it that I have 3 sub-circuits in my circuit now, and I can power gate, for instance, factor 2 and 3, turn them off, power gate them by power transistors. And as a result, I would have factor 1 running, and that's gonna give me the least power consumption, but also the accuracy is not gonna be good. If I want to have more accuracy, I can enable factor 2, and that's basically going to be ORed with factor 1, and that's going to produce better results, but at increased power consumption. And then ultimately, I can turn on factor 3, that's giving me highest accuracy, and it's going to give me the highest power consumption. So that way, actually, we can dynamically control how many factors are turned on, and that allows us to trade off accuracy and power. So here's a simple example before I turn to bigger circuit. This is a circuit called X2, very simple circuit. It has 10 inputs, 7 primary outputs. So basically a truth table has about 7,000 bits. And if you look, if I just do the first factor in here and look at the error versus the power, you'll see that I have a Hamming distance of 15%. And that's basically like, you're basically, that's the minimum power you get. As I turn on more factors, F is equal to 2, 3, 4, 5, 6, I start reducing my Hamming distance. The outputs now look very closer to the original circuit, but at the same time, I start increasing the power. But you can see that there's a huge power range in here. So basically, I can dial down my power by 6x and increase the error accordingly. So that technique allows us to give us that idea that I was talking about a few slides earlier, that we can do scalable or adaptive operation of the error versus the power. So you might be wondering, this looks all good, but how about bigger circuits? I mean, this idea is built on building a truth table, and I can only do that for smaller circuit. How about big ones? It's not a big deal, because I can take a large circuit and I can divide it into smaller sub-circuits, say with hypergraph partitioning, which is a very mature algorithmic technology. And I can subdivide the circuit until each one of them has a small enough number of inputs to build a truth table, and then I can basically start approximating each one of these sub-circuits and stitching it back into the main circuit. In the paper, we talk about, what's the order of the sub-circuit, how big it is, how much approximation you should do to each one, but I don't have time today for a lot of these details, but I think maybe just get you the gist of the idea that you can partition and approximate each sub-circuit. We have an open source tool actually that does all of this. It's called BLASYS. It's available on GitHub. You're very welcome to try it. It builds on existing open source tool, of course, plus our own work. And the flow in general is that you can just put your circuit in Verilog. You write it in Verilog, just any Verilog. And as long as it's basically, we synthesize it by Yosis. We create the AIG graph out of it. And then we do the hyper partitioning there to create sub-circuits. And then for each sub-circuit, we build its truth table. And then for each truth table, we do the binary matrix factorization, and that creates the compressor and the decompressor circuits. And then we synthesize these compressor and decompressor circuits with ABC, which is a tool for logic synthesis. And then we plug it back into the original circuit. And then once you plug back a sub-circuit with an approximate sub-circuit, you're ready to calculate the error, because you shouldn't be calculating the error of a sub-circuit in isolation, because you have to look at how the error in the sub-circuit translates into your primary output. So you have to plug it back into the original circuit to figure out the error and ultimately the chip area. And then, you can continue doing this. And we have a design space exploration approach that, try to intelligently pick which sub-circuits to approximate and so forth. But that's the basic idea in there of this tool, BLASYS. This is some results in here from some circuits that are typical in these domain applications. A butterfly structure you'll see in DSP, a perceptor.
Quick question, why the name BLASYS?
I think it was Boolean level approximation system. That's how it
Okay.
was. Yeah.
Okay.
And then, yeah, we have the butterfly, an example from DSP. We have like a perceptron circuit from machine learning. We have a sum of absolute differences in computer vision. It's a very popular circuit for detecting like motion between different frames in videos. And we have a 4-tap FIR filter. This is the original design areas, the areas on the power and the number of IOs. The way we do this, instead of having it based on factorization, instead of telling you, okay, here is the power at different factorizations, I picked factorization that gave me 5% error and 10% error. So I think this is more what designers maybe were looking for. So in here, basically, you can enable factors to have 5% error, oh, sorry, 10% error, and you can enable additional factors to reduce the error and give you 5%. And this is the power consumption savings you get compared to the baseline. So you can pretty much cut your power almost by half or more than half, and still be within, you know, 5 to 10% error. Go ahead.
Quick question. So when you quantify the accuracy, are you just doing dynamic simulations or?
Yeah.
Okay.
So in this, we have two works. In one of them, we're doing basically dynamic simulations. And the reason is, you know, these are big circuits anyway. There's no formal proofs for them. And I don't have a chart for that, but typically, like, right, I mean, when we all design our Verilog codes for hardware, you typically have some test benches. So the same test benches that people use to verify their designs would be the same test benches that you would use to calculate the QR, or the quality of results of the approximate circuits. And I think that's reasonable enough.
Yeah, I'm just wondering if you could get, you know, occasionally like an error that basically causes things to lock up and stuff like that, where, because obviously not all errors are equal, but just matters if you happen to catch a very serious error or not.
Yeah. So there is in here, first of all, when we apply these, we only apply them to the data path, the approximate components, not on the control. So okay. That's why all these circuits, we don't touch the control. It's only in the data path. So that's one way to mitigate that catastrophic error problem. But nevertheless, there is, I think, room for people looking for topics in approximate computing to kind of bound the worst error. There's definitely techniques that can bound the worst error for individual arithmetic unit, like that multiplier case that Jose was asking. I can bound the error in that technique, for instance, that Jose mentioned. The error is twice, and then you multiply them with 4x at worst case. But if you have a general circuit, how do you bound the error? That is not clear. So right now we have test benches. Somebody has some, yeah. So we have.
So there is a question. Are you going to answer this question? So someone asked, at which level do we check the error? You know, do we only check it after we're done with the final circuit, or do you check errors, I guess, from the compressor and decompressor?
Yeah. So the idea in here, for instance, if I do the compressor and the decompressor, if I just evaluate the error on that truth table, then I'm evaluating the error of the sub-circuit. But where's the sub-circuit? Like, imagine the sub-circuit, what, for instance, was the adder in the most significant path of your multiplier. Maybe the error is small there. Maybe I put a small error. But if you look at it from the big circuits, it's in the most significant bit part. So basically, if I don't embed the approximate sub-circuit back into my original circuit and look at the error in the final, then I could be into big surprise at the end of the day. But that said, it doesn't prevent you from using heuristics. Maybe if you take a sub-circuit and you approximate it and the error is horrible just for that sub-circuit, maybe it's a good idea to not approximate it, because it's already horrible at the local level. So even if I plug it in on the global level and look at the output from the whole circuit, maybe it's not a good idea. So that's some of the, you know, I didn't talk about design space exploration part, but we have some discussions on that. There's also some work on approximate computing that basically tries to come up with heuristics, like, you know, try to assign weights to different nodes and gates in your circuit. So when you can basically do like a traversal in your circuit to begin with, you can assign weights or values for the different nodes in your circuit. And basically some of them could be don't touch, or if you know that if I touch this one, it can lead to a big propagation error. And then I can use this as some kind of a prioritization when I do the approximation. So all the nodes all the sub-circuits with these high impact nodes, basically don't approximate them, don't touch them, and just go approximate sub-circuits that don't have any high impact nodes. So there's some work in that area. So there's definitely room there. Good questions from the audience. Any more questions? All right, so that's how we can do general approximate synthesis techniques. I'm going to talk about one application specific deep neural networks. And the reason I want to talk about it, of course, it's very popular. I don't think there's anybody can come give talks now without a deep neural network part in it. But the other thing too is that, once you know the application, you can do some of these software, hardware, co-design techniques. So definitely DNN is one of them. So I'll review some of our work. We had a few papers starting in 2017 in that area, but this field is very fast moving. So so some of this might already look like it's outdated, but it actually was fairly recently published. All right, so I have a deep neural network, and how can we do this dynamic trade-off between the accuracy and the computational resources to power the approximations? And the deep neural network is approximate anyway, we know that. So the first thing we've done is we designed the architecture. I told you at the beginning, hope I convinced you that the best thing to do these approximations is within accelerators. So we designed an accelerator for a neural network. It's a pretty much basic design you follow in the literature. You have a number of neural functional units that run in parallel. Each one also run the multiplications and addition, inside the for the synapses in parallel. You have input buffers that hold the activations. You have weight buffers that hold the weights. The results are basically flowing systolically through this neural functional unit. They get stored in an output buffer, and everything at the end goes to the main memory. And we've designed this, and we did not tape it out. We just designed in TSMC 65. And basically, we get about 100 gigaflop per watt. If you look at your typical GPU from 65 nanometer, which is kind of old now, you get about 5 gigaflops per watt. So again, this is not any surprising result. Everybody knows that if you design an accelerator, it's going to beat CPUs and GPUs in terms of energy efficiency. The key idea then is what kind of approximation you do. So we looked at a number of approximations that could be done. This was published in DATE 2017 and DAC 2018, or I think DAC 2000, DAC 2018 and DATE 2017. So we looked at different approximations. For weights, you can use fixed point weight. You can use power of 2 weights. If you use power of 2 weights, basically the multiplication just becomes shifts. So that's a big improvement. You're basically getting rid of all these bulky multipliers and replacing them by barrel shifters. You can ultimately have binary weights, which just boils down to adding and subtracting your activations. For the activation themselves, we looked at fixed point, different precisions, and also dynamic fixed point. So the difference between them, that in a fixed point, the point for the radix between the integer and your fractional part is fixed. With dynamic fixed point, this point could move depending on the layer of your activation. So you just have to keep track of where that point is. And it gives you extra accuracy at the expense of a little bit more power. So when you take the accelerator that I just designed before, and the starting point is, say, floating point 32, and you start substituting them by fixed point 32 and 32, meaning the activations and the weights are 32 bits, fixed point 16, 16, fixed point 8, 8, powers of 2 in here. So you have 6 bits for the shifting amount and 16 bits for the activations. And then finally, there is binary net where the weight just have 1 bit. It's a plus or a minus 1, and 16 bit for the activation. So you can see that, as you apply these approximations to your precision, you can dramatically cut down the power consumptions by going down to almost 15 or 15x between the base case. And of course, if you look at all the GPUs coming out since that time, 2017, 18, they now have inference engines that are basically just using 8 bits integer, int 8 in them. And that's good enough for inference, which is the target in here. I'm not doing something for training. It's mostly for inference. All right, so the basic idea for software hardware co-design, and I had the reference in here, I'm sorry, it's a paper from Carbaro basically. And the idea in here is that, let's say for instance, you want to do the power of 2 network. How are you going to find the weights for your neural networks? If you just trained an original network and chop the weights, like approximate each weight to the power of 2, you're going to get horrible error. The way basically you train these neural networks, these approximate ones, let's say the idea is to kind of maintain 2 copies of your network. One is the floating point and the other one is the power of 2 point. You train the original floating point network as usual. Then you approximate the weights to the nearest power of 2, and you don't stop. You evaluate the error that results from the smaller network with the power of 2, and then you basically pretend or propagate this error to pretend it's coming from your floating point. And then you do the back propagation algorithm, and you keep on doing this for a few times. And if your smaller network is good enough, meaning it has approximations that can handle the data, then this should converge and you will get a good set of weights that reduce the error. That's basically one of the main ideas in there. So we thought that, okay, sorry, if we can cut down the power consumption by 10, 20x, for instance, like in the case for power of 2. Power of 2 is almost 10x in here from the floating point. I cut down the power consumption by 2x, and then I use this training process. I recover most of my error, but it's not perfect. Your power of 2 network will still have error difference than the original network. What we can do is we can deploy them in an ensemble. So instead of using one small network, using one small power of 2 network, we can use few of them. Let's say we use 2. And then you look at basically the outputs in there from the softmax and you average them and you make your prediction based on those 2 networks. Now, what is the difference between those 2 networks? The difference between those is that the initial weights were initialized differently from different random. So basically, and they're trained separately. So their final set of weights are different. So this is called kind of ensemble boosting, where you basically take the 2 network and boost their accuracy. And in here, yes, I will increase my energy consumption or my power consumption by twice, but hey, I actually had 10x room to begin with because I made it approximate. So that's basically this idea that I was saying early on, that after I can do the approximation, I can basically try to go back and compensate for the error and retain a good chunk of my power. So for instance, here is the results. I have x-axis with a semi-log scale and classification accuracy on the y scale. This is the CFAR with the AlexNet. Similar results are for ImageNet in our paper. You can see the floating point 32-bit up in here. That's the black one. And you can see the original approximations, the ones in here, the fixed point 16, power of 2, 16, fixed point 8 bits, power of 2 with dynamic floating points. And you can see, for instance, let's take the power of 2 with dynamic floating point for the activations. You can see that that gives us a huge improvement in here on orders of magnitude, like I think maybe 20x over the floating point. So I definitely have a lot of margin. So I can deploy an ensemble of 2 of those networks. So basically that's the arrow that goes up in here. So now I have a power of 2 dynamic floating point network that runs in an ensemble. And its power is much less than the floating point, and their accuracy is even higher than it. So basically, we're getting, you start to wondering is, why did I even have the floating point to begin? Or why did I have the fixed point? So if you look at the fixed point, even in here, fixed point even 8.8, it still has higher energy consumption, maybe 2 to 3x in that semi-log scale, and less error. So we even have room than int 8. If your int 8 is your default, we're still getting better result with this technique.
So the very, very neat numbers and idea. Now, one quick question. Is the assemble compensating all the way, like, for example, maybe it's layer 2 who needs something with more precision. It's not all the layers. So I'm saying something, or maybe it's the edge of the picture that it needs more precision. Have you looked at to see if it's like random distribution, the weights all over, or is it focused in some areas?
It's an interesting idea. No, we just duplicated the whole thing, but what you say makes total sense. Like, I want to try it and see what we get. It's, yeah, we just took the network, we just trained 2 separate instances of it, and that's it. But if everybody like sees in here, what Jose is suggesting, he's saying, what if, for instance, like the first few layers are good, we don't need to create an ensemble of them. We can fix them, and then we just create an ensemble, say, out of those, last 3 layers, for instance, or the last 2 layers.
Or maybe there is a special, maybe it's on the edges of the picture, maybe it's on the center of the picture, I don't know.
Yeah, maybe there's no reason to duplicate everything or to ensemble everything. There could be some partial ensembles that are better. Yeah, definitely interesting idea. Yeah, thank you. Any questions so far? So what we wanted to do is something similar to what you suggested, but it's not like what you're suggesting is different, but we wanted to do something that's a little bit dynamic. So for instance, like, why do I always have to run 2 the ensemble? Maybe 1 is good enough. Okay, so it's kind of like trying to what you're trying to achieve what you're trying to say by reducing the overhead, but it's from a different angle. So here's what we're doing in here. We basically this is my deep neural network, say the dynamic power of 2. I load first the weights for the first one of my ensemble. And then I look at the output, and somehow imagine you have you're an oracle and you have this glass bowl, and you look at the output and you say, the output is not good enough. And if it's not good enough, let me load the weights for the second DNN in my ensemble and calculate the result and average them. And you can even continue saying, the second output is not good enough, or the combination of the first 2 DNNs are not good enough. Let me go run it one more time. until you're satisfied and you say yes. So that's basically the idea that we were trying to do. It's kind of like that factor idea, right? I'm gonna run a portion of my circuit, and I'm gonna look at the result, and if it's good, I will stop. If I want to get better accuracy, I will run additional components in my circuit and get better accuracy. All right, so what would be that oracle? So that oracle, we call it meta reasoner, because it's reasoning about the computations. It's reasoning, it's like a high level controller that's reasoning if the computation is doing good or not. And what is that meta reasoner is basically doing? And the idea basically in the literature is to look at something called the score margin. So the score margin, you want to look at the output, say, of the soft layers. You look at the difference between the highest two classifiers. You look at the highest two outputs and look at the difference between them. When your classifier is working properly, you're going to see one output that's very high, like say the picture of some dog, a bulldog, and then everything else is very close to zero. So when you look at the distribution, it's going to look like this. Is basically that one neuron that's basically firing very high will have a high difference compared to all the other ones. So the difference is high. So you get that distribution in the left. That's an indicator that you have a correct inference. So when we basically inspect the output and we see something like that, we say, okay, that's good enough. We don't need to run another round of DNN. However, when the classification is not good, you're going to look at the output of these soft maxes, and basically they're all kind of like, there's not one that looks like high. Everything looks kind of within the same level. So when you subtract them, you see a lot of numbers close to zero. So you see kind of an inverted distribution like you're seeing on the right-hand side. So when you see the distribution on the right-hand side, that's a wrong inference. So that's basically our meta reasoner. Our meta reasoner is looking at the output from the soft maxes and looking at the score margin. And if it's above a certain threshold, then it says, okay, that's good enough. We don't need to run another round in this DNN ensemble. We're just going to be good with one DNN, but if it's not good, we're going to run more. Now, when you apply this technique on this results in here, you basically can save 23% of the energy. Of course, that meta reasoner is not like a perfect oracle, so you end up losing a tiny amount of accuracy at 0.1, but nevertheless, you're saving quarter of your energy. So I can take, for instance, in here, the results from this ensemble up in here, and I can save quarter of my energy, and I'm basically just like, my accuracy is almost the same.
So I have a question. Do you do batching here?
I don't remember, actually. I do think we do batching in here, but I have to.
Because if you do batching, the numbers can interfere with each other on the accuracy. So you might have to rerun the whole batch, no?
Yeah, I see what you're saying. I don't remember, actually. I have to look back at the paper and see what you're doing. Because yeah, I mean, is it like when it's doing a batch, is it some of the images are good in the batch and some are not good? That's what you're hinting at, right? So in that case, we're
yeah, exactly that.
Yeah, if you're doing one image at a time, then it's perfect. If your batch size is one, it's perfect. But if your batch size is big, then it's a problem. You could be wasting your time in here. So I have to look at that and check. It's a good point. Any questions about this dynamic ensemble? So that's an additional way to reduce energy. Let's see, there's a question. Which logic design the output inference table? I'm not getting that question on the chat. With which logic we design the output inference table? What is the output inference table?
Maybe does the person want to clarify if I allow them to talk? P-data?
Sorry, results. Oh, output inference result is just a command in here. I'm not saying that like output, like declare the result, declare the inference winner. So basically, you know, you look at the output from your final neuron classification, you do this subtraction. You don't need to do it everywhere because it's going to take a while. You don't want to do like a quadratic complexity, just do a sampling in there. And basically, if you see something towards the right, there's basically one classifier that has a high output and everybody else is low, or most of the other ones are low, or a sample of them is low, then basically it looks like it's a good hint, it's a good classification. But if you start things starting to become fuzzy, then in that case, you run another round. Output inference result, like basically, if you see that pattern in here and it was a bulldog, basically a classifier that says that's the bulldog, then in that case, you say, okay, it's a bulldog. Otherwise, you basically have to run more. So over time, you can think about it that if you were doing a bad job in your classification, you start with something like on the right, you're making a wrong inference, but you start adding more DNNs in your ensemble, and then it starts switching towards something like in the left, basically by virtue of this averaging and making the prediction accordingly. That's basically like the logic of it. Good. All right, so the last thing I want to talk about is the end-to-end system co-optimizations, and I want to look at one particular system, which is wearables. So in wearables in here, I have a sensor input, which is a gyroscope, and it's a 3D signal for X and Y and Z. And in that low power wearable device, you do feature extraction based on these waveforms. Then after you extracted the features from the waveforms, you do a classification, which is using a DNN. And then based the DNN outcome will tell you whether this person is walking, standing, climbing up the stairs, going down the stairs, running, and so forth. So if we apply this idea of the DNNs on the classifier, what about the rest of the system? Well, actually, if you look at these low power end-to-end systems, the sensor itself can take between 40 to 50% of the total power. So this means that if I just play with my DNN in the classification section and use approximate circuits, say with the synthesize approximate circuit for the feature extraction, which I'll show you. Basically, the feature extraction part is very similar algorithms like the one I had for the general circuits, FIR filters, and some of absolute differences and so forth. Then in that case, I'm kind of relatively restricted. I mean, I'm only changing the power half of my system, and I'm leaving the sensor out of the picture. So can we do something for the sensor? Can we also scale the sensor in a very similar way we've done the computations? And yes, this is, for instance, a sensor of one of the devices we use. This is a very low power device. And if you look at the sensor, you could actually configure the sensor. And the sensor could be configured by changing its averaging window and the sampling frequency. And that's the consumption of the sensor in microamperes for each one of these pair configurations. And the assumption, of course, is that if I use a bigger averaging window and a higher sampling frequency, I'm getting better signal, tracking signals from my activity or from my gyroscope. So in here, you're looking at the same idea. I can basically change the power consumption of my sensor by 20x from going from the lowest combination in here, 6.25 hertz, up to 100 hertz. And I can change the power consumption in there, and as a result, the accuracy. But when you look at the sensor by itself, that's not good enough. What we want to do is to look at the sensor in the context of the end-to-end system. When I change the sensor configuration, what happens to the human activity recognition error? What happens out of my pipeline? So the pipeline in here, we're having basically for feature extraction, extract some statistical features from these gyroscope signals, such as the averages, the standard deviation, and the fast Fourier coefficients from it. And then the classification is just based on a neural network that's trained on this feature extraction. And we basically pool the data from all the different configurations to train this classifier. So that's interesting. The classifier can handle whatever sensor configuration you throw it on it. It will still give you good tracking. So what we've done is if you look in here, we have 5 sampling frequencies and 5 averaging windows. So we have 25 operating point for the sensor. We took each one of them and we basically looked at the end-to-end to accuracy through this pipeline that I mentioned. At the end of the day, how good I am. Did I classify walking correctly? Did I classify running correctly? And then basically what you're seeing in here on the y-axis is the recognition accuracy of 6 human activities: the walking, the standing, the running, going up, going down, and sitting, idle, doing nothing. And I'm looking at the power consumption of the sensor. And you can see in here that despite I have all these different configurations, really only 4 ones that are mattering. The 4 ones on this Pareto frontier, these are the ones that give me the optimal trade-off between the sensor power and the accuracy. So if you're designing a controller to adapt your wearable, you don't need to think of all this big space. I just need to move things, dial things along this Pareto frontier. And by doing this, I can basically crank down the energy consumption, the power consumption of the sensor by 10x. And at most, I get a hit of about 2.5% in accuracy, roughly from 98.5% to about 94.2%. So we've decided to do the same idea. We have a meta resonator in here. We have the sensor, we have the human activity recognition engine, that's pipeline that I mentioned. And then we look at the current activity, we monitor that, and that's the input to our meta resonator that basically look at the current activity and accordingly adjust the average rate and the sampling frequency for the sensors. So what is the meta resonator doing? The algorithm we're having is that we're monitoring the activity. And if the activity is relatively stable, then in that case, it gives me an incentive to cut down the average rate and the sampling frequency, dial down, move down on this Pareto frontier in here. And if I see that the activity is unstable, meaning things have been changing by the user, then I go back up in here to the highest setting. I basically say, okay, the user is doing something different. Let me go crank up the setting as much as I can. So this is, for instance, an example in here to summarize the result. We're getting in time in here. This is, for instance, output from the real sensor in here. The person is actually sitting at the beginning and then starts walking. Now, the activity recognition pipeline will tell you at the beginning it's sitting and will tell you it's walking. So when in our method in here, here's our adaptive method. At the beginning, everything is at the highest setting. You know, I have the averaging window high and the frequency, the frequency is 100 Hertz and the averaging window 128 samples. And then over time, I see the user not doing anything. Everything is just sitting. So I start cranking down the settings along this Pareto frontier until I have the least power consumption. So that allows me to save me power and I'm not sacrificing any error. Then suddenly the user starts moving. So I start seeing that my activity pipeline is giving me a different recognition. It's telling me that the person is walking. So I start, okay, I need to pay attention in here and I crank up the settings of the sensor to the highest level. And I see that the person walking, it hasn't changed, so it starts dialing down again. So that's the main idea for this approximate computing method. We're trying to basically couple this adaptive operation with the sensor, and the sensor itself, like I said, it's approximate, right? Because if I change the frequency and the averaging window, I'm producing an approximate signal in the process. So if you do this kind of end-to-end approximation optimization, you can get 70% reduction in power because you're doing it dynamically. You get a very small amount of error degradation and basically happening during the transitions, because the sensor is at a lower rate in here where you first transit. When you first see that the signal is walking, there is a chance you do a little bit of incorrect classification in here. But once you crank up the settings again, then you're going to do a good activity. Obviously, it's a function of how often does the user change their behavior? So for instance, if the user has like medium activity level, then in that case, the error would be higher. If the user doesn't have a low activity level, then in that case, the accuracy would be lower. But on the average, you're getting 70% reduction in power end to end for the whole system at 1.5% degradation. So that's the summary in here. I hope I convinced you that this intersection between data-rich application, accelerators, and approximation, you can really get big reductions in energy consumption. Big wins there. And there was this recurring idea in the slides that hardware computations could be broken up and you can basically boost the accuracy by adding these components. We've seen this idea with Boolean matrix factorization. I can add up those factors by ORing them, can improve my accuracy and accordingly, of course, reduce power. We've seen it with DNN ensembles. I can do the same thing there. Then we've seen that we can, if you know the application, like in case of wearable or dynamic deep neural networks, we can now have those meta reasoners, basically a controller that reasons about the computation that's happening and decides to adapt the hardware dynamically. For DNN, it was the score margins. For wearables, it was the activity instability, an activity that's changing. We've also seen that we don't need to exclude the sensor. The sensor as itself produces signals that are approximate of reality. And if we change the configuration of the sensor, we can incorporate the sensor in this approximation game, and we can even do co-optimization and give larger savings. These are just quick references for people who are interested in the papers that describe some of that work. And that's it. That's all what I have today. Thank you guys for joining.
Very nice. Thank you.
Yeah, that's pretty cool.
Thank you.
So if any students have any kind of questions, feel free to raise your hand if you want to talk or type them in the question and answer thing.
We had a good number of questions during the talk. I thought all the questions were nice from the audience. There's one question coming in.
Actually, we have one question. So what is the runtime of your synthesis thing scale with design size? You mentioned you had a heuristic that kind of hierarchically did stuff, but.
Yeah, so that's a good question. So the bottleneck really in the runtime, it actually comes from this last step, the hardware error simulation. Everything is pretty quick. When you have your design, you parse it with hypergraph partitioning, that's fast. you look at each partition. If it's small enough, you can do the binary matrix factorization. You can approximate it, synthesize it, and plug it back. The biggest time consumption in the whole process is the simulation of the error. Because when you plug back the approximate sub-circuit into the bigger one and you simulate your entire test bench again, that's a problem. So this is kind of like, that's really what limits the error. So in our papers, we looked at the trade-off between the test bench size and how accurate you get as a result. So we tried to really crank down the test bench size to be as small as we can. That still gives us a meaningful, error quantification. But that's the rationale there.
It's interesting. I wonder if you could do like, when you talk about the dynamic simulation for error stuff, I was thinking, can you do formal verification of this with allowing a certain number of errors or something? Not exact equivalence, but
yeah,
equivalence plus a Hamming distance, right?
Right. Yeah. I mean, there's definitely room. There's definitely room in that area for some interesting ideas to come up there.
Yeah.
Yeah.
Yeah, we have one more. Pete, I'll let you talk.
Hi.
Hi there.
Hi. It was very nice talk, and I have just one question. Like in the initial level of the slides, you showed that the graph between Hamming distance and the accuracy, where you showed that there is 10x improvement with more power. I mean, where the power is more and then accuracy is taking more. Like you had a graph with the factors. Like if you are increasing the F value.
This one?
Yes.
Yeah.
So I was just trying to correlate with this one with where you showed in the last with that fixed point and floating thing, like to explain the accuracy and the data. Like my question is how, yeah. So like how you are going to, have optimized like the trade-off. Yeah, I'm not sure.
I missed the question. So what is like in here in this particular plot? What is the
Like here we can see that we are compromising the power to get the accuracy, like almost accuracy, and here it is like 6x. Sorry.
Yeah.
And so in the later slide we saw that there was a discussion on floating points and fixed
point? Yeah.
Yes. So my question is like with this factor, like by increasing this factor and by using the DNA network, like what maximum we can, can we really reach to the maximum accuracy? Like if we
Okay, yeah, good. I think I'm getting to, yeah, I think I'm trying to see your picture. I'll say something in here. So there's a few things. I just want to clarify something to the audience that I talked here about Hamming distance, but that's not the only error metric we use. In fact, in here, in this one, we're actually using the arithmetic output. And the reason is basically very simple. We're using test benches. So in the test bench, you're free to use whatever Q bar quality of result metric you want. If you want to use L2 forms, you want to use peak signal to noise ratio, you're free to use whatever metric you pick. So it's not like BLASYS only works with Hamming distance. In fact, in BLASYS, you create your own little function. If you put, yeah, in Python, there's some background noise. Yeah, all right. So in BLASYS, you basically define for every benchmark the QOR function, the Python function that compare the output. So you're free to choose whatever metric you want. That's one thing. Now, with respect to this case, there's actually a little red dot up in here. This is the original accurate circuit. If you use the full circuit in here, this is the result. So basically, f of equal to 6 is very close to the original circuit, and things starts going down afterwards in terms of power. Now, we actually have another work we haven't published, so that's why I not mentioned, but it basically says that if somebody if somebody wants to bring you the accurate design, like imagine you turned on the factors like this, and that's all great. But what if I actually want to have the accurate operation? We actually have a technique we haven't published yet that basically adds another box in there, another circuit that we call it the corrector. And that corrector will flip any bits that are in error. It's designed to do that. So I haven't talked about this, but we do have the option to have full accurate operation if we want to. Not just inaccurate. Now, in some way, actually, the other one is kind of, this is the fixed point, is kind of has the same trend, but the reason is very simple. Again, you're doing more approximations, so you're getting a smaller area, smaller power. So it's basically going down in a very similar way to the other one, despite that the tools that we use to create these approximations are entirely different in both systems. I hope this kind of answers the question.
Yeah, I was just asking like how much accurate you can be with this technique.
Yeah,
Right?
so I think, yeah, that's it. Yeah. So I have a paper we haven't, so you've seen in here how accurate we can get with this one is very accurate, but like I said, you can, the small number of bits at the end that are flipped, you can still flip them by adding this corrector circuit, but I haven't talked about this since it's not published. Yeah.
And also we can do the testing, like we can do that error checking at any point, like in the case of dynamic one, we can do the checking at any point and it can be corrected to the like 100% accurate.
Yeah, I mean, the idea is I tell you the idea. The idea, let's say in here, I've done that approximate truth table. I have it in here, and I know that these bits are flipped. Well, I can basically design a circuit that for each one of these inputs will produce one in here that gets XORed with my approximate circuit. So that corrector circuit is actually XORed with the approximate circuit. And anytime I basically see an input that should flip this bit, I basically create one and flips it. So it's very similar. You've already kind of came up with the idea. You know, intuitively, but that's the idea of it.
Thank you so much.
All right. Yeah, I think that's good. If there's any last minute questions, otherwise we'll let you. Oh yeah, Scott.
Yeah, I had one. So thank you again for a great talk. As you discussed, you know, there's many different applications. Different applications may be more or less tolerant of approximation. Your work has proposed many ways of providing these approximations. Do you have any big picture, high level insights into what makes certain applications at a circuit level, not so much the application level, what makes them more amenable to approximation? Is it something about the structure of their topology, something about the information redundancy or something, or is it too hard to guess that in big picture?
I mean, yeah, I mean, it's, I have it in here, yeah. I personally feel like when the algorithm itself is approximate, that's, I feel like when we often get a big bang, like, you know, because, and also people's like appetite for it, it's kind of becomes okay, right? Like, you know, when I tell you it's a DNN with a classification accuracy of 80%, I'll give you something with less the power and it's 79.5 or almost 80%. People would say, yeah, okay, it wasn't guaranteed to be optimal anyway. But then when you have a circuit that is maybe a little bit tighter, then you might be hesitant. Like I didn't show this. We have results, for instance, on doing it on FFT, and you actually get pretty strong peak signal to noise ratio. But you know, maybe sometimes people in signal processing would be a little bit kind of anxious to do it. And that's why I usually like to talk about the end-to-end system, because I feel like when I talk about the end-to-end system, people get guarantees that if I embed this approximate modules, at the end of the day, I'm doing like still a decent job. That's the rationale. But yeah, in terms of like what you're saying, I feel approximate algorithms is a big one. There's another big class of applications we're all familiar with approximate algorithm is basically graphics. When you play a video game, you choose the graphic settings, you know, high, low, shading, blah, 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 and you can play your video game and it's not a big deal for you. You know, you're still having a good time. But it's not necessarily, it's just, I mean, I would think it's a data rich application, but definitely computer graphics is a big one that can't tolerate this amount of error, and it's been exploited there forever right now in computer graphics since forever.
Great, thank you.
Yeah, thanks.
All right. So with that, thanks for giving the talk. We appreciate your time.
Yeah, thanks a lot for all the great feedback and great questions, and for having me, guys. Hope everybody have a successful semester or quarter, I guess, in UCSC.
Yeah, we're done next week with the quarter. So.
All right. Thanks a lot, guys. Take care.
All right.
Yeah. See you.
Bye, everyone.